as beautifully set the stage by Visweshwar and other speakers on the ISM and scattering schemes aspect of the observations. I'll be talking on the other spectrum where you have a binary system and how the binary companion interacts with the pulsars emitted photons which reach us. So, yeah, in terms of transients like FRBs, we have motivation to look for such aspects, such objects in our Milky Way galaxy itself. For example, some of the FRBs have 16-day period with 5-day orbital period on active region, and similar for other FRBs. Some of the polarization studies they have shown RM fluctuations, and the others the flare-like events which show these are mostly ejected by the companion of the pulsar, and they show imprints on the dynamic spectra and polarization properties. So these are the motivational things why we should look for the polarization behaviors in the binary systems of the Milky Way galaxy. Yeah, so the observations taken for this experiment was taken from parts, and this is a wide UWL receiver from 700 to 400 gigahertz coherently redispersed. The pulsar is 5 milliseconds with a 10-day orbital period, so 30 seconds of subintegration would encapsulate thousands of pulsars. So stability is not an issue, and the frequency resolution of the data is 1 megahertz with 124 subints along the orbital phase. So jump into the analysis. I'll just have a quick recap of pointer sphere, and I want you to emphasize on the fact that so IQUV are the 4 spots which we get from the observations, and this F is basically the fractional polarization of the total fractional polarization, which will be useful in the upcoming slides. So yeah, so once you have QUV, you can plot it in the 3D diagram, and these are the angles which are used to plot this. So this is from this is the representation applied to one of the pulsars which have clustering of different colored points are basically different points in the phase space, spin phase space, which means the clustering implies different components have nearby clusters in the QUV plane. So coming back to this is the full plot. I'll explain each of them in the upcoming slides. So the first row was the dynamic spectra, which shows spots I for 20 minutes subintegration, and y-axis is the frequency channels. So this is time versus frequency, and this is let's say if you have a 10-day 10-hour observation period. So the first, second, third columns are basically the first 20 minute, middle 20 minute, and last 20 minute of the observation. So this is the 4 spots and the L observation. So this is the dynamic spectra. We have the profile as well. So you have 1024 pulses, and you have spots IQUV profiles. The dotted lines, the dotted points are the main component for this pulsar. These are the spectra where you have the x-axis, the frequency in megahertz, and y is the fluxes. And again, so this one, so this is for one time subintegration. Yeah. On the y-axis, each of the column represents the dynamic spectra, the profile, the first, middle, and last 20 minutes of the observation duration. Now, for each 20 minutes of sampled in different orbital period, we have such plots, and Okay, so last thing is the pointer sphere. We just have, for the sake of distinguishing between the magnetospheric effects and other effects which I'll be talking about, we just put the main component and add that onto the pointer sphere. So this is the, I'll show what the row means, but yeah. So if you compose all of the plots in one plot, then this is the first 20 minutes, this is the middle 20 minutes, this is the last 20 minutes. This is the average of all the three components, and this is the dynamic spectra. And the last column represents the corresponding QUV pointed on the pointer sphere. Yeah, so now we have an orbital period. Now, obviously, you have RM variations along the orbital phase. So this is what the RM correction done for the observations at different epochs. So we have four epochs for this pulsar, and we have the RM variation across the orbital period. Now, going back to the plot which we have the spectra for each of the time chunk of 20 minutes. The fact which we observed was first that the polarization is always, for the main component, it's always positive. There is no swap in the angle across the phase bins. So that's one thing. The other thing is there is slight changes in the peak of the Stokes eye. The Stokes eye, it's changing with the frequency as it orbits the different orbital phase. So this is one of the phenomena already there in the literature known as gigahertz turnover spectra, where you have different orbital phase which have the spectral turnover changing with the orbital phase. We want to probe the polarization aspect of this phenomena, and that's why we want to look for the spectra of QUV. Now, if you want to see so the thing which we observed was that some orbital phases, the U flips the sign from positive to negative after RM correction. So to quantify that, I take the spectra of QUV and correlate with the Stokes eye spectra. You see there is these two boxes represents, okay, so this row basically represents the first column represents the Pearson correlation, which is where we normalize the variance of the Stokes eye QUV correspondingly, which takes care of the scintillation into account. So we have a plus minus one, a normalized scale of comparing it between the epochs. So that's one thing. And the other thing is the p-value. That gives us a control of how confident are we on the observed correlation values. So if you see in the, so we have two of the observations separated by few years where we have similar nature of Stokes U flipping a sign on the same orbital phase. So that's something which is observed for the first time. And so this is the green dots are the correlation between U and I, spectra of U and I, and others are relatively stable compared to U, but the U has a significant change in the spectra, and we believe that's because of the magnetized plasma ejected from the companion along the orbital phase. So this is the turnover, gigahertz turnover frequencies plotted for different orbital phases. This is just for one epoch. We are still in the process of doing it for other epochs. And this is a previous study which shows the orbital phase which dependence on the turnovers. So that's the other thing which we did was to look for the counterpart in other spectrums, and we only found the counterpart reliably in the DESI DR10 legacy survey, where we see this is a pointing and have a clump of gas which has a structure like green on one end and the red on the other end. So we'll have a follow-up observation on that, but this is just the optical counterpart which we observed in the survey data. So the takeaway message from this is we do observe mini eclipse kind of situation in other binary orbital observations, and if we have the magnetic field, strong magnetic field either from the ISM or the binary companion, we have a magnetized region where we have sky plane magnetic field, and that can actually cause something called due to generalized Faraday rotation, you can have a conversion of QUV, and that's what we are seeing in the polarization, and which is a very common thing to probe in the extragalactic sources. So yeah, this is one of the galactic sources where we can see polarization changes due to companion. Yeah, so that has been my thanks.
Thanks, Rahul. Questions, comments for Rahul?
Hey, hi Rahul. Thanks for that talk. You briefly mentioned there was sign change after doing some kind of RM correction. So just a very naive question, what kind of correction are you applying on it?
Oh, so we have these RM from the, so there is a technique where you search for the RM, and it's like a DM correction but in the QU plane along the frequency axis. So if you have some RM where you have, what does RM do is basically what you receive is not actually the QU signals from the object. So you basically mix between Q and U, and that causes oscillations of Q along the frequency axis. So in order to find that, you take a Q square plus U square, and basically add along the frequency axis. So any oscillations, if they are taken out and then added, that will cause a peak, and that's how you find the one of the techniques where you find the RM. There are other techniques where you take Fourier transform of the Q, but that's different. So this is one of the things that's how I figured out the RM and then applied the RM on the QU.
Okay, got it. Thank you.
Other questions?
Hi, very interesting talk. I was curious if this technique, was there a reason why you chose this pulsar, or are there other pulsars you have tried to
So we have
look at?
checked for 1939, which is a spider pulsar. We don't see such flips along the orbital period. So we are still probing, we are expanding our samples, but yeah, so this is one of the pulsar where we observe such change of, yeah.
And this one, okay, so, and is this a black widow or a red back?
No, this is a 10-day orbital period pulsar.
Okay.
A millisecond pulsar. So
Okay.
we chose this pulsar because the duty cycle is quite large, and on further experiments, we would like to see other components as well. So this is just the main component, and in order to distinguish between the magnetospheric effects and other effects. So since the flip, there is no flip along the, so usually the Q, profile Q has a plus and minus variation along the pulse phase. We don't see such things, and that's one of the main reasons we chose this pulsar, so that we can average and see what actually is going to the binary system instead of the magnetosphere. That's one of the reasons we chose this one.
Okay, thank you.
Then let's thanks Rahul. I think there is no question for online also. And all the other speakers of the sessions.